Chemical equilibrium. A reaction that is in the state of equilibrium is where there's both the forward reaction that produces the products and the reverse reaction where the products will go back to becoming reactants. When there's balance between the two reactions, that is what is called equilibrium. At equilibrium, the rate of reaction of both the forward reaction and the reverse reaction must be equal to each other, so both reactions happen at the same time with the same speed. For a reaction to be at equilibrium, there are a specific set of rules that needs to be kept. 1. The solution must be in a closed system. None of the solution must be able to get out, and nothing must be able to get in, because that would then disturb the balance of the equilibrium state. And 2. There must be both reactants and products. The equation that is used in calculating the equilibrium constant looks like this. K is equal to the concentration of products to the power of the coefficients divided by the concentration of the reactants to the power of their coefficients. The value of the fraction is called Q, and when Q is equal to K, then that means that the reaction is at equilibrium. So when you, for example, increase the concentration of one of the reactants, then the value of Q will go down and will no longer be equal to K. So therefore, at the exact time you add the extra reactants, then the reaction will no longer be at equilibrium. When you look at Le Chatelier's principle, it says, if one or more factors that affect the equilibrium is changed, the position of the equilibrium shifts in the direction that reduces the change. So basically, when you change the concentration of one of the products or reactant, that is, then it will try to even out the change that you made by making a shift to the direction that will do exactly that. Now the experiment that we did was iron 3 ions and thiocyanate, which would produce iron 3 thiocyanate. The equilibrium expression for the experiment would look like this. K is equal to the concentration of iron 3 thiocyanate divided by the concentration of iron 3 ions times the concentration of thiocyanate. The first thing we did in the experiment was making our equilibrium mixture. The mixture consisted of iron 3 nitrate and potassium thiocyanate. The iron 3 ions is a yellow solution, while the thiocyanate is a colorless solution. But when we mixed the two solutions, it then produced iron 3 thiocyanate, which is a red solution. The rate of the reaction was very fast because it didn't take long for us to see the color change. The solution was then poured into 6 test tubes. In the first test tube, the stress was that we would increase the concentration of iron 3 ions. And then we saw that the color turned into a darker red, which was the iron 3 thiocyanate. When we look at the equilibrium expression, we can see that when the concentration of iron 3 ions goes up, then the value of Q will be smaller than K, and the solution is no longer at equilibrium. Chatelier's principle says that the reaction will make a shift to the direction that would even out the change. So in the first test tube, there's a shift to the right, so it would produce more products. In the second test tube, we then increase the concentration of the thiocyanate. What happens in the second test tube is pretty much the same as in the first test tube. When the concentration of thiocyanate goes up, then the value of Q will again be smaller than K. The solution turned darker red as well, which means that the reaction made a shift to the right. Before we could start with test tube 3, we did a small test in another test tube where we mixed iron 3 nitrate and ascorbic acid. Ascorbic acid reduces iron 3 ions to iron 2 ions. So when we added the two, we saw that the solution turned colorless, because iron 2 ions in aqueous solution is colorless. So in the third test tube, the stress would then be to decrease the concentration of iron 3 ions, because the ascorbic acid reduced iron 3 ions to iron 2 ions. When the concentration of iron 3 ions is decreased, then the value of Q will then go up, and then K is smaller than Q. So according to Le Chatelier's principle, the reaction now made a shift to the left, because the reaction to the left would then produce more reactants and would even out the change. In test tube 4, we added a few drops of silver nitrate. The silver ions from the silver nitrate would react with the thiocyanate ions and form a precipitate. We could see that the solution turned less red than the original equilibrium mixture. When the thiocyanate reacts with the silver ions, then the concentration of thiocyanate decreases. And when that happens, then the value of Q will go up and K will now be smaller than Q. So there is a shift to the left to again even out the change. In the last 2 test tubes, we changed the temperature. In the 5th test tube, we increased the temperature. The forward reaction is an exothermic reaction, and then the reverse reaction must be endothermic. An exothermic reaction releases heat, while an endothermic reaction consumes heat. So when we increase the temperature, there will then be a shift to the left, because the endothermic reaction would even out the change in temperature. But the equilibrium constant is affected by temperature, so when there's a shift to the left, then we would now have more reactants and less products. So the value of the equilibrium constant will go down. In test tube number 6, we decreased the temperature. To even out the change in temperature, there must be produced more heat, which would be the endothermic reaction that releases heat. So there is now a shift to the right. The value of K will now go up, because there is a shift to the right, then there will be more products than reactants.